Alright, so today we're going to talk about a physics problem called one rod, one particle, one axle. We have it set up here. Essentially, this square denotes a wall, a horizontal plane. And hanging from the wall, or rather attached to it, is an axle. And then hanging from that axle is a rod with a particle attached to the end. And this rod is free to rotate, and as you can imagine, gravity has an effect here. So if you hold it here, in this current position, it is going to be inclined, as this arrow denotes, to swing counterclockwise, and if it's given enough initial velocity, it may be able to reach this top unstable equilibrium wherein it's resting in this vertical position. So this is our problem, and let's go over the relevant details, and then let's lay some framework for the topics that are in play. The physics concepts. So we have a rod here of mass 4m and length L, and attached to the end of it is a particle mass with mass m. Now it has no volume, it's just a particle. It is a finite point right here with all of its mass in one specific point here at the end of our rod. So particle mass m, and here is our initial position. It is parallel, the rod particle assembly is parallel to the ground, and it is released from rest, and as it is released from rest, simultaneously it is given some initial velocity v naught. And as it seems here, the v naught is actually enough, as it's combined with gravity, to be able to swing all the way around and reach this vertical unstable equilibrium. So that's our setup, and then our question asks us to give all answers in terms of m, r, and nature constants. Oh, sorry, m, l, and nature constants, l being the length of the rod. So let's talk about the concepts that are in play here. One of the important concepts is Newton's second law, which we've repurposed for rotation. Many of us are already familiar with the concept of force equals mass times acceleration. Well, this concept can be repurposed for rotation and torque. And what we can say is that torque, which is essentially our force, torque equals rotational inertia times angular acceleration. And what is rotational inertia? Well, essentially, it's very similar to the inertia that you might see in a block problem, where you have some block and some velocity. It's its inclination to keep rotating, the same way that linear inertia is some block or some linearly moving object's inclination to keep moving. So again, it's force equals mass times acceleration, but now it's torque equals rotational inertia times angular acceleration. Another important thing that we need to understand is the idea of energy conservation. And there's this important equation that's worth understanding, and you can pause this video if this doesn't make sense. But essentially, it's that the work done by non-conservative forces are things like friction, air drag, things that are taking away from the movement of the system essentially, and things that care about the path of motion. So work done by non-conservative forces has to equal the final energy within a system minus the initial energy within a system. Now, if there's no non-conservative forces, that means there's no work being done by non-conservative forces. That makes sense. And in that case, work done by non-conservative forces equals 0. And when there's no non-conservative forces, then we can move one of these energies onto the other side of the equation and essentially say that the final energy equals the initial energy. So just to have some more concise, specific bookkeeping here, we want to account for all types of energy, kinetic energy and potential energy, when we worry about having no energy being lost. So what we can say here is that we can say the final linear kinetic energy plus the final rotational kinetic energy plus the final potential energy equals the initial linear kinetic energy plus the initial rotational kinetic energy plus the initial potential energy. And when we talk about potential energy, we're mainly worried about either springs or gravity. But I don't see any springs in this problem, so it looks like we'll just be worrying about gravity here. And two more important things to talk about that are going to be pertinent for this problem and really for any torque or rotation problem is the concepts of torque and the parallel axis theorem. So what is torque? Well, for example, here I've got my laptop. If I want to close my laptop, I can't apply a force right at the hinge. That doesn't give me enough.
Season in 10 years. Northwestern's looking for their 5th 10-win season in school history. Pat Fitzgerald is third as a...
I had college football on there. If I want to close this, if I want to close my laptop, I cannot apply a force right at the hinge. What I need is leverage. I need to move my force further away from the hinge and apply it here. That way, I'm able to close my laptop. So what happened there? What was that distance? So what can we refer to that distance that I created as? Well, essentially what we're going to call it is we're going to call it the moment arm. So just to explain real quickly, let's grab a piece of paper here and talk about what is a moment arm really quickly. So let's say that I've got the ground here and I've got this block and I pull it this way, and that's my force. The direction of this force obviously matters, right? Because if I were to push this way, the movement would be very different than if I were to push this way. So here, this is our direction of force, and this entire direction is our moment arm. That's the direction of the force is what our moment arm is. So here, what forces are we worried about here? Well, we're just worried about gravity. And where is gravity being applied to a rod? It's being applied at its center of mass. And where is that center of mass? It's not going to be right here. It would be if there was no particle attached at the end. But since there is a particle, it's going to be offset, and it's going to be somewhere here. And that's where our gravity, force of gravity, is being applied. And in terms of the direction, well, that's very important too. And it just so happens that with gravity, it's always pointing down. And that makes sense because however an object is oriented, whether this is like this or however it is, it's always going to be inclined to go directly downwards towards the ground, towards the earth. So our force of gravity is going straight down here. And this is our entire moment arm, or rather, our direction of motion, or the direction of the force. So now what we need to figure out is what is the shortest distance from this force line to our rotational axis. And since it's just vertical, it becomes quite simple. It's simply going to be however far away the center of masses of the rod is removed from our axle. Because this right here, along the rod, this line is the shortest distance. Now, if it would have been in an angle, perhaps if I had a force that was going like this, then the shortest distance would be here. And we would need to worry about it that way. But that's not the case. So we have a perfectly perpendicular force of gravity here, and we just need to worry about that. That is the R in this torque equation. Torque equals force times R, or force times the distance of the moment arm. And what is the force? It's gravity. And gravity here is going to be dictated by the total mass of our assembly, which we'll discuss is 5m. It's 4m of the rod plus the m of our particle. So that's torque. And then the parallel axis theorem. What is the parallel axis theorem? What that does is that helps us determine the rotational inertia of a system. So in a perfect world, perhaps our pivot point would be right here in the center of mass of our object. And let's just say that it was just the rod. That'd be a much simpler equation because then we would just be able to use the information given in the problem, wherein it says that the rotational inertia of a rod with an axis through its center is 1/12 ml squared. That would be a much simpler problem, but that's not the case. We actually have our rotational axis some amount removed from its from the rod's center of mass. We're not going to worry about the particle for the moment. We're worrying about the rod. So what that means is that we would have the 1/12 ml squared here, but then we would need to add in or factor in how far away our rotational axis is removed from the center of mass of whatever we're worried about. So we have the mass times the distance, or h, from the center of mass squared. And when we have a more complex system like this, we can simply add up the rotational inertia of each constituent, and that will give us the total rotational inertia of the assembly. So this is very important to understand, and if you need to watch this a couple of times, that's fine, but it's very important to understand these topics to be able to tackle really any sort of rotational problem, whether it has rotation, torque, both, with an Atwood's machine or with something like this. Very important to understand these topics. So now that we have this framework in place and we have our problem set up, let's go to the 4 questions which are provided to us here. And this would be something like you would see in a first semester physics course in college. Actually, this was a question from my first semester physics course. So let's go through these questions and let's use our problem and our framework to tackle them, and it shouldn't be too hard. Question 1. Determine the rotational inertia of the assembly about the axle. Now remember, as I said, if we want to find the total rotational inertia, I total, we just add up the rotational inertia of the rod to the rotational inertia of the particle. So we already talked a bit about this. Let's start with finding the rotational inertia of the rod. We have our center of mass element. Would it have been a much easier problem in a perfect world? Well, we already know, again, rotational inertia of the rod with the axis through the center is 1/12 mr squared. So we have that down here, and then we add to it mh squared. And now let's substitute in some of the information we know. 1/12 ml squared, m is asking for the mass. Well, we know that the rod mass is 4m, and L is asking for the length, and we know that L is just simply L. So 1/12 times 4m times L squared, plus, again asking for the mass, 4m, times the distance that our rotational axis is, how far it is removed from the center of mass. So we know that that's L over 2, because again, we're doing this piece by piece, just worrying about the rod here, not the particle. The center of mass of the rod alone is, well, in the center of the mass, because we have a uniformly dense rod. So it's right here, and that means that we are half the distance of the rod away, which is L over 2. So 4m times L over 2 squared. And then we can add this all up, and this is the most tough part, or at least of this portion, is just getting all the relevant information, and then we simplify it down, and you can pause this video at any point to be able to double check if I made a mistake or something, but I don't believe I did. And we get that the rotational inertia of the rod on its own is 4/3 ml squared. And we're saying little m because that is the variable that we're using to denote our masses in this problem. Next, we find the rotational inertia of the particle on its own. And this one's a little bit more tricky. Since the particle has no volume, only mass, it wouldn't be inclined to rotate if we had the rotational axis through its center. So what that means is that the I center of mass would actually be 0, and we're only worrying about the mass times how far away it is from the rotational axis. Again, this might be a little bit complicated, but you need to think about the idea of rotational inertia, the idea of momentum. How inclined will this be to move? And its inclination has nothing to do, or rather would be deleted by having this through its center of mass, because it has no volume. So it wouldn't, it wouldn't want to rotate about that. So again, with this, it's a little bit different. For the I particle, we're only worrying about the mh squared. And again, the h is how far away its center of mass is removed from the rotational axle. What's the mass? We know that's just one little m. And how far away is it removed from our rotational axle? Well, since the axle's at one end of our rod and the particle is at the other end, and we know the rod is length L, It's just L length away from our rotational axle. So it's mL squared. So now we have our I particle and our I rod, and we're just going to add those up. We're going to say mL squared equals 3/3 mL squared, 4/3 mL squared equals 4/3 mL squared, and we end up with 7/3 mL squared. So that is our collective rotational inertia, the rotational inertia of this entire assembly about this axle. Question 1, not too bad, just tackled it. Question 2, I miswrote it a little bit here, but what it says is, what is the initial angular acceleration? So what's it asking? Essentially, as this is released from rest, simultaneously it is given some initial, I'm sorry, my mistake, that's the next question. For this question, what is the initial angular acceleration? For that, we reference Newton's second law. My mistake, I didn't mean to be confusing. So, question 2, what is the initial angular acceleration? For that, we go right here to Newton's second law for rotation, which is that torque equals rotational inertia times angular acceleration. Well, I just care about angular acceleration here. These are pertinent, but I want to isolate this. So what I'm going to say is angular acceleration equals torque divided by rotational inertia. Torque divided by rotational inertia. So we already found a rotational inertia of this entire assembly, which is 7/3 mL squared. So we're halfway done with finding our fraction here. And now we need to find torque. And what is torque? It's the force times the length of the moment arm, like we said here, like we earlier discussed. So we already know that the force is going to be 5 mg. And that's because that's a pretty simple physics concept. That one's pretty easy to understand. The larger that an object is, the more powerful the gravity will be. That makes sense, right? So 5m is our collective mass of this assembly, and then g is our gravitational constant. So that is our force, 5 mg. But then the torque, well, we got to think, where is the force of gravity being applied? We already said it's going to be applied somewhere around here. And the distance, or the r, is going to be how far away the entire assembly's center of mass is from our rotation axis. So what are we going to do there? We're going to use a little trick. We're going to create a number line from 0 to L. 0 is here, L is here. 0 is here, L is here. And what we're going to do is we're going to create this little number line, and we're going to add up the mass times the position of every element over the mass. So here we have m times 0 becomes 0. Here we have 4m times L over 2, because remember, the center of mass of the rod alone is in the center of the mass, is in the center of the rod since it's uniformly dense. And then the total mass, as we said earlier, is 5m. So m times 0, nothing there, plus 4m times L over 2 over 5m. We've got a lot of m's that we can cancel out here. This 4 times 2 ends up being 2 up here, and what we end up with is 2L over 5, 2/5 L. I jumped around a little bit fast there, but if you need to pause it and work it out on your own, I suggest that you do so. But again, what's important is that we get the right pieces in place, because the simplification is not the hard part. The hard part is figuring out what information is relevant, what facts of nature do we need to know, and how can we take facts that we do know and compile them and manipulate them into finding the facts that we want to know. So now we've found our center of mass. We've said that it's 2/5 L away from 0. That's away from 0. The 0 is how far 2/5 L away from 0. Well, 0 is our particle. And I don't really care about how far away it is from the particle. I want to know how far away our collective center of mass is from the rotational axis. And what we can say is that if it's 2/5 L away from 0, that means that it's 3/5 L away from L. Or rather, away from our rotational axis. And that's what we care about. So what we can say is that it's 3/5 L away from our center of mass. Our center of mass is 3/5 L away from our rotational axis. So now we have everything that we need. We know that angular acceleration equals torque, which is going to be 5 mg times the length. Here it is, 5 mg times how far away it is, which is 3 over 5L. We can cancel these 5's out, and we end up with 3 mlg. That is our torque. And then we put that over our rotational inertia, which we already found, 7/3 ml squared. Do a bit of simplifying. I suggest you do this on your own. And we end up with the angular acceleration equaling 9g over 7L. Not too bad. Question 3. I jumped to this earlier. Now we're going to talk about our initial velocity. Question 3. What is the angular speed needed for the assembly to reach the vertical position? So if we give this too little initial velocity, it's not going to be able to reach all the way up here, and it's going to stop somewhere before then, and then it's going to swing around and then stop here. All right, if we give it a little bit, it's just going to go like that. Give it a little bit more, it might go like that. But if we give it enough, it'll swing all the way around and reach a resting point here. So for questions like this, what is the speed needed, things like that, that should kind of make you think about energy conservation, because we have no non-conservative forces. The only thing acting is gravity, and gravity is a conservative force. It does not care about what your path of motion is. It just cares about your starting position and your end position, right? If I've got my pen and I move it all around, it doesn't matter. If I start here and I end here, then the difference in energy is just the ending point minus the starting point. It doesn't matter what I do, right? So here we can say that we have our bookkeeping here, right? The total kinetic energy final plus the total potential energy final equals the total kinetic energy initial plus the total potential energy initial. So what do we need to do here? Well, first we need to create a reference line for our gravity, because it's very important. Gravity is all referential, at least in problems like this, right? If I have no gravity here, then that means that I have, and then I'm up here, that means that I have L more gravity, right? So what do we want to do? We want to create a gravitational line that makes this problem as easy to solve as possible. So what I propose is that we say at this point, for just easy bookkeeping purposes, that there is no gravitational energy, there is no potential energy. All there is just the initial angular speed. And then at the end, since it comes to rest, there is no angular speed, there is no kinetic energy, there's only potential energy. So we're going to say initially there is only kinetic energy, and at the end there's only potential energy. And that might be a little bit complicated, but again, we think about the idea of a gravitational reference line and how gravity itself is referential, especially in problems like this. I'm going to set my gravity line here. Okay? It's going through our rod. So how far above the center of mass of this assembly is relative to our gravitational line? It's right there. It's 0. So it has no potential energy. At the end, it's all the way up here. So our gravitational energy is going to be dictated by how far above the center of mass is of this assembly relative to our gravitational line. And again, we know that the center of mass is going to be somewhere up here. And how far away is it? Well, it's the same distance that it was before. It's going to be 3/5 L. So that's our final height. And again, it's very important. We have the total mass, 5m, times our gravitational constant of nature, g, 5mg, times the height. So it's mgh, mgh. Another important pattern of nature, and pattern that you need to be able to understand and conceptualize in this problem and for future problems. So mgh, we have our initial kinetic energy times equals our final potential energy. And what is our initial kinetic energy? It's going to be 1/2 times the rotational inertia, which we've already found, times the angular speed, omega squared, which we're trying to find, so we'll want to isolate that later, equals, so that's our kinetic energy, equals the final potential energy, which is 5m, total mass, times g, constant of nature, times h, how high it is away from our gravitational line, which we already said is 3/5 L. We do some simplifying, and again, this is the hard part. We've done the hard part now, and we understand how we got there. And if you didn't, then rewatch this or pause it and try to work it out on your own. But we got there, it should make sense, and now we simplify it, and we end up with omega squared equaling 18g over 7L. And if we just want omega rather than omega squared, then you just take the square root of both sides, and you end up with omega equals square root of 18g over 7L. And that should all make sense, right? That's not too hard to understand. So, easy. Omega equals square root of 18g over 7L. On to our final question. Question 4. When in the vertical position, what is the torque magnitude around the axle applied to the assembly by gravity? Oh, okay. Kind of weird wording, but essentially, what torque is being applied to our assembly by gravity? All right, and again, what is torque? It's the force times the distance of the moment arm. Well, the force is always going to be the same, right? Because the gravity, or no, my mistake. The force is not always going to be the same. But in this case, in this vertical position, our force of gravity is similar to what we found earlier, right? It's 5 mg 3/5 L. That's the potential energy. That's what it is. We've already found that. But now we need to say, what is the distance? What is it? We found our force, but what is the distance of its moment arm? Well, remember, the moment arm is the direction of the motion, or the direction of the force. And we want to find the shortest possible distance. Well, in this case, remember, gravity always points downwards, directly downwards. Our moment arm distance is 0 because our direction of the force goes right through our rotational axis. So what that means is that however big this object is, whatever the other things are, however big this force is, the R is 0, and anything times 0 equals 0. So what we say is that it is 0 here. And that's it. This might have ended up being a little bit lengthy, had a little mishap with some college football, but hopefully this helped anybody watching this better understand how torque and rotation come into play in elementary physics problems. And once you understand this framework and you understand a few basic applications of this framework in the context of a simple problem, it really becomes powerful in how many ways you can manipulate this information and apply it to some really interesting problems that you wouldn't think you'd be able to tackle, but now you can because you know the important information. So yeah, thanks for watching, and catch you next time.